and a warm welcome to all. Today is our guest, Professor Ajinkya Nilawar. He is an assistant professor at Ramjababa College of Engineering and Electronics and Communication Engineering department. He is here for a GET lecture on Prerna scheme for SC/ST students for higher education. Uh, he has total 7 years of experience. Of that, 2 years of industry experience and 5 years of teaching experience. He is completed his MTech and currently submitted his PhD in the field of image processing. Not taking so much of time, I request to Professor Ajinkya Nilawar sir, please kindly proceed for the lecture.
Okay. Thank you so much, sir. Now I'll continue with my lecture. So basically, today's lecture we will see with some digital modulation technique, digital modulation schemes which are used in communication field. Again, whenever we are uttering the word communication, communication is derived from communic. Communic means transferring information from one end to another end. So in any communication system, what exactly happens? There is one source, one transmitter, then channel, then receiver. Then whatever signal we are sending from transmitter, channel, receiver, we are getting as it is signal at the end of the receiver. So this is what the broad aspect regarding communication. Again, whenever we have to send information from transmitter to receiver, we need the modulation concept. Again, there is a question why we use the modulation scheme for deciding height of an antenna. We are using the modulation scheme. So basically, the formula for designing height of antenna is lambda by 4. You know, whenever you are moving around, either in Nagpur city, either you are moving from Nagpur to out of city, you are observing so many towers, which is consist of some electrical towers which are connected with wires. But there are some tower beside which P kind of thing is there. So these towers are used for communication purpose, and these towers are useful modulation scheme. So for whenever we are uttering the term modulation, you always understand that modulation means with the help of antenna, we are modulating the input signal. So for deciding that height of antenna, we are required the modulation. So depend on the input, the modulation schemes are given. The first is continuous wave modulation. Here you will see CW stands for continuous wave, and second, the pulse stands for the pulse scheme. So continuous wave modulation, we are having input as a sine wave. Inside the transmitter, the signal processing will happen, and inside the channel, again, sine wave along with another wave is traveling from transmitter to receiver. That means carrier will carry the basic information. So again, carrier wave is high frequency signal, and our baseband basic any information signal is baseband signal is having the low frequency than the carrier one. And then with the combination of this carrier and baseband signal is passed through the channel, and it will get at the receiver. So there are various modulation scheme as far as continuous wave is concerned, that is amplitude modulation, frequency modulation, and phase modulation. So any signal having three attributes, that is amplitude, frequency, phase. What do you mean by attribute? We can play as an engineer, we can play with only three attributes. That means we can change only three attributes of any signal. Either we will change amplitude, either we can change frequency, or either we can change phase. If you are observing the CRO and function generator arrangement, you know that. So whenever signal is generating from function generator, suppose 1 kilohertz, 10 volt peak to peak signal is there. With the help of CRO, there are two knobs. That is, first knob consists of volt per division, from which amplitude of a signal can adjust it. Amplitude is nothing but in the two-dimensional signal, whenever we are representing the voltage. So we can adjust voltage with the help of volt per division knob. Second thing we can adjust is frequency. That means width of that particular signal on the x-axis we can arrange it. So if you are increasing time per division knob, the signal on the CRO get shrink, and if you are decrease, then it expands. So shrinking and expanding is nothing but increasing and decreasing the time period. Time period deals with the frequency as t is equal to 1 by a. So just I want to say that any signal having three attributes. First is amplitude, second one is frequency. That means volt per division knob, time per division knob, And third, we can change its phase. For observing phase difference on the CRO, we require external phase shifting circuitry. In the EDC, you have already studied the RC phase shift circuit. So such kind of arrangements are there for shifting the phase. So basically, in continuous wave, we are having amplitude modulation, frequency modulation, and phase modulation. That means we can change its attribute, three attributes. So this is deals with the amplitude modulation, or we can say the continuous wave modulation. But in today's topic, we will deal with the digital communication. So what is basic difference between analog and digital? It's simple. If the input to the system is sine wave, then it is analog communication. If input to the system or the whatever the signal is presented inside digital communication. So it is a complete a play what the waveform they are present inside the channel. If inside the channel, that means from transmitter to receiver communication with the help of sine wave and carrier wave, then it is analog communication. If the communication between transmitter and receiver with the help of digital signal, but obvious that we are having only two digital signals, 0 and 1. So digital communication, that means digital means what? 0 and 1 signal, and communication means what? Communicate. That is communication between transmitter to receiver. That means we are sending and receiving digital signals inside the channel with the help of transmitter and receiver. In that case, digital communication will happen. Now, what are the different digital modulation? What do you mean by modulation? But obvious that it is deciding height of antenna, where this antenna is placed at the end of transmitter and at the start of a receiver. So basically the communication will happen between transmitter to receiver means what? Antennas of transmitter and antennas of a receiver. If the communication it is in the form of digital signals, that is in 0101 form, in that case we are using the digital modulation scheme. What are the digital modulation scheme? Basically, the pulse modulation consists of digital modulation and again analog modulation. So in digital modulation, we are having PCM stands for pulse code modulation, DM stands for delta modulation, and in analog, we are having pulse amplitude modulation, pulse position modulation, and pulse width modulation. Just I'm giving you the brief idea regarding what do you mean by pulse analog, how it will look. Consider this is a sine wave. It is represented as x of t is equal to a. A is nothing but its amplitude. So here from this position to this position, that means positive to negative, we are having some amplitude. In this direction, that means in the x direction, it is represented as t. That is t is equal to 1 by f. And hence mathematical equation we can given as x of t is equal to amplitude. That means this position to this position multiply by nature of a signal. So this signal is start with the sine. Hence the amplitude A multiply by sine omega into t. What is t here? This is time period. T is equal to 1 by f. So mathematical representation says that this is the signal of amplitude. Since it is starting with the 0, it is a sine into omega into t. Okay. Then these are some pulses. That means this is the carrier which will carry information. If the pulse modulation in analog form, the PAM look like this. Okay. Then PWM look like this and PPM look like this. So this is not a concern with our syllabus. So directly we move to our today's basic topic, that is pulse code modulation. So basically pulse means what? And just from the diagram you know that what do you mean by pulse? Pulse is nothing but a square wave signal having some amplitude. So this is what the clock pulse with the help of in digital electron. What do you mean by clock? Clock is generated and these are the pulses which are used for communication purpose. So in the case of digital communication, pulse wave are our carrier. In the case of amplitude modulation, high frequency sine signal is our carrier. In this case, clock pulses are our carrier. That means carrier will carry the information. The second thing is the code, and third thing is the modulation. You know, the pulse means the train of pulses. Code means whatever signal we require, it will convert it into a certain form. It is considered to be code. And M stands for the modulation. Again, this is again modulation scheme, which is where it is used at the end of transmitter with the help of antenna. We are sending the signal. So inside the transmitter block, we are having three different blocks, that is source encoder, channel encoder, and lastly the modulation. So the last block of the transmitter where antenna is connected is nothing but the modulation scheme. And in that modulation scheme, we are selecting PCM whenever input to that particular transmitter block or the modulation block is digital signal. So generally, whenever we are talking with each other or whatever signals we are having, they are in analog form, whether it is audio signal, whether it is video signal. Okay. Generally, what are the different types of signal we are using day-to-day life? That means what are the signals you are dealing in the mobile? You can talk, that means audio signal. You can see, that means video signal. And you can use your internet data. So for using that internet data, we are having different concept called CCN, Computer Communication Network, in which we are having various protocols, ISO, SI model, TCP IP model. All these things are related with the digital thing where data is encapsulated in the packet. But in the communication scheme, we are dealing with the audio and video data. Okay. Consider a few years back, we are having only landline phone. What we can do with that landline phone? We can just talking with each other. So that means audio signal transmission can happen. Then the mobile generations come in 1G, 2G, 3G, 4G form. In the 1G form, we can send MMS to each other. That means texting can enable. In the 2G and 3G, we can send some pic file, that means pictorial file, with the help of MMS. Okay. In that, whenever we are having 2G, the facility of WhatsApp is not there. So as soon as 3G is coming, it is possible to send and receive images and short video file. And nowadays we are having the 4G where we can stream online the video. So this is how the data transmission can happen. So in 1G we can communicate with each other with the audio signal. That means only audio communication is there, and the modulation scheme we are needed is only digital side. Whenever we are moving toward the video, the advanced modulation schemes are needed. So it is started with PCM, and you can say it's first generation mobile which we are using 1G. In that case, we are using these kind of schemes. Nowadays also the BSNL where FTTH connect layers are there. That means in the remote areas, we are still using PCM kind of arrangement. If you are visiting the BSNL, they are considering this for this modulation scheme for far long areas. So what is basically pulse code modulation? It is a simple technique where we are converting analog data into digital data. Okay, you may say that, sir, we are having ICs, right? ADC 8080 or 0808, from which we can convert analog signal into digital signal. Then why we are needed the PC? So the basic concept is whenever we are having IC is having a certain input. Suppose 8-pin IC, then only 2 inputs are there. Suppose 16-pin IC, then 4 inputs are there. But whenever we are communicating with audio signal, it is continuous process in which the conversion required in faster manner. Like now I am talking to you, you are listening my voice, but it is happening the conversion. That means my throat is generating frequency in digital form with the help of my laptop, and then that data, digital data, is transferring with the help of internet, right? I am using now my net, whatever geo mobile I am using for in wireless technology. You are using also some landline kind of thing or wireless kind of thing. Again, it is digital conversion. That means my mobile will convert, or my PC and mobile will convert my voice into digital signal. That digital signal pass through the internet. That means in the channel block consists of internet, and you are receiving the signal it is all this data conversion in very faster manner. That means in nanosecond and picosecond, so that you are getting you assume that you are getting my voice lively. But so many times it happens, it is having some delay. In so many times we are observing the delay. If we are live streaming match, if we are live streaming some videos are there, then that delay can be considered, or we can experience that delay. So just I want to say that whenever data is traveling from one end to another end, data conversion takes place continuously. Hence, that IC concept is not used here. That means we can't use any kind of IC. Definitely in the transmitter, we are having various blocks which consist of ICs, but this is what continuous process where we are converting our analog signal into digital signal. Okay. So the pulse code modulation, the input is analog signal. Again, this is particularly deals with only audio signal. We are not dealing with the video here. Okay. So as far as the concerned and as far as gate syllabus is concerned, we are considering only audio signal. Okay, what is range of our voice signal? 300 hertz to 3000 hertz. That means 300 hertz to 3 kilohertz. So we are dealing only with these frequencies only. So whenever analog input is there, sine wave, it will ranges, it is having frequency from 300 hertz to 3 kilohertz. So that much frequency we are dealing with. Then the first step for this PCM is the sampling. Second step, we are having its quantization. And third step, we are having the encoding. This is most commonly asked question in the gate. What are the steps are there in PCM? Or consider the following sequence and tell what is the correct sequence for PCM. So what are the options? Sampling, quantization, encoding. The option may be changed. Quantization, sampling, encoding. Third option, encoding, quantization, sampling, and fourth, all of the above. But the correct answer is only first, always there is a sampling. Second is quantization. Third is encoding. So as far as gate is concerned, this PCM point is most important because there are so many numericals, there are some theoretical concepts. And as I already mentioned, there is a twisting in option that's saying that, but the question may like that, uh, in the PCM, what is the second step? Whether options are sampling, quantization, encoding, none of the above. So what is second stage? Definitely it is quantization. What is first stage? It is sampling. And what is third stage? It is encoding. So always keep in mind SQE. It is sampling, quantization, and encoding. These are the three basic steps we are using in PCM. Okay. Then what do you mean by sampling? So you know the nature of a sine signal, right? It is starting from 0 and it is having certain time period. So it will look like this is what our sine signal. So what is the role of sampling? Sampling is cutting the signal. We can say I'm always using the word chopping the signal. So chopping means what? Just like we are chopping our vegetables, the sampling will chop the entire signal. What happened after the chopping? After chopping, we are converting that signal into its mathematical equivalent voltage form. As I already mentioned, since it is sine wave, if I want to change the amplitude, what we are doing on the CRO, we are just moving or using that volt per division law, right? So similarly, for deciding the voltage, we are using quantization block for deciding the different voltage levels of a chopped signal. What is chopping is nothing but the sampling. And last is the encoding. Encoding means representing data into digital form. So one by one we will see what are the parameters. So keep in mind, pulse code modulation is a digital modulation scheme. It consists of three basic blocks, that is sampling, quantization, encoding. Sampling is nothing but the chopping out the signals. Second is the quantization, which will gives us a voltage levels, that voltage levels decided in quantization block. And third one is the encoding, which will represent the quantized signal into digital form. So what do you mean by digital? Digital is nothing but a representation of signal in 0101 form. Okay. So these are three basic things which we are using in pulse code modulation. So first one is the sampling. Technical definition says that a continuous time signal can completely represented in sample form and recovered back from the sample from frequency is greater than twice of f max. What is f max? F max is the information signal frequency. Just take an example. Consider sine wave with frequency 300 hertz. Okay. Then what should be the sampling frequency? As per the sampling formula, Fs is equal to twice of Fmax. So sampling frequency at the first sampling block, we will require a greater than twice. That means if my signal is 300 hertz, then sampling frequency should be 600 hertz, minimum 600 hertz, more than it, you can utilize it. So sampling theorem says that the sampling frequency always greater than twice of f max. But in simple language, you can say that suppose we are having three input 10, 20, 30. So what is maximum value? 30. Then sampling frequency should require it twice of 30. That means 60. For 10 also there is a 60. For 20 also there is a 60 sampling frequency, and for 30 also there is a 60 sampling frequency. So f max represents, suppose there are n input, a maximum value for the frequency. Suppose there are n input and maximum value is fm, that is f max. The example is same. We are having three signal, 10 hertz, 20 hertz, 30 hertz. So what is fm? 30 hertz is my fm. And what is sampling frequency I will require? That is the 30 multiplied 2. Same sampling theorem says that always sampling frequency is greater than twice of f max. So this is how we are calculating the sampling frequency. Then there are three different types or three different methods which we are used as per that. So first one is the ideal. Here you will see that how this ideal will chop out the signal. So it is simple one arrow arrangement. Definitely, if you are going to the hardware side, it is a simple arrangement of diode and key. We are passing the signal to the diode, key is open, then key is closed. Again, key is open, key is closed. That means signal is passing through the hardware circuitry at the regular interval. That interval is 1 microsecond, 2 microsecond, and 3 microsecond. So such kind of there is. Just I'm giving one example, simple example how this sampling works. Suppose whenever suppose we are having function in our home and there are 15 people around our front door. Then in our capacity of our home at a time 2 or 3% will be entertained. So what we are doing? We are opening door for 10 minutes. For 3% will come, then we are shut down the door. Whenever this 3% will move out, after that we are again opening our door, again allow 3%, and whenever this 3% will move out, then we allow next 3%. So similarly, the sampling will do the same thing. For whatever time we are deciding that sampling, suppose 1 second, 2 second, 3 second, that key will open. It is a simple switch. Switch will open for 1 second, then close, another 1 second, close, another 1 second, close, 1 microsecond, 1 nanosecond. So depend on how much sampling we require, depend on that we are, on hardware side, we are using that particular circuitry. Again, that key opening and circuit arrangement depend on which frequency we are dealing with it, right? So the sampling we are having three different types. First is ideal, second one is natural, third one is the flat top. As far as digital communication is concerned, we are most of the time dealing with flat top sampling. Okay. So the what is flat top sampling? The flat top sampling, the signal will start this at bubble. Where you will see the bubble, the signal will start. Then a finite duration time signal is generated. That means pulse is generated and it will end. Another suppose this signal is consider second bubble, consider the second bubble start for some clock pulse. Then our signals are generated with the help of flat top sampling. Okay. So flat top sampling, same question in the PCM, which type of sampling is used in PCM? Your answer is flat top sampling. And there may be question, these are three different signals, X1, this, X2, this, X3, this. What should be the sampling frequency if we are using the digital modulation scheme? It is simple. If it is given 100 Hz, 200 Hz, 300 Hz, what should be the sampling frequency? Definitely whatever maximum frequency we are having as the input signal, multiply by 2. It's our sampling frequency. So this is taken quantization. Okay. Quantization, here you will see we are using one parameter called S. S stands for the step size. The step size mathematically given by higher voltage minus lower voltage divided by Q. What is Q? Q is nothing but quantization level. So quantization level decided by 2 raised to n. The value of n is 2, 3, 4. Now, what is this quantization? What is step size? How it will look? Okay. So consider our normal sine signal and then suppose this is what x direction and y direction. Okay. Whenever we are having x direction and y direction, suppose this is the entire block. What should be the step size? That means where I will draw the line. So that line drawing is nothing but our step size. And how many lines should we draw here is decided by this n factor. Suppose this is the entire block and my value of n is 2. That means from 0 position to ending position 2 raised to 2, 4. That means I will draw only 1, 2, 3, 4 lines. Suppose 2 raised to 3, 8. That means I will draw 1, 2, 3, 4, 5, 6, 7, 8 lines. So drawing of this line, that means deciding quantization level is depend on this n factor. And this step size, what should be the step is given by this VH minus. Then if I want to write here voltage level, then 0, 1, 2, 3, 4, 5, 6, 7, 8. Right. If 2-volt difference is there, then 0, 2, 4. So deciding that voltage is depend on this quantization level. Again, whenever we will do the quantization, this is what our sine. I think this is you are getting or not getting. I don't know. Just I will move my cursor. So this is my sine signal. Whenever I will generate a quantization, it is having some step size. So generation of staircase is nothing but my quantization. So this is my original signal, the continuous line, and this staircase is my quantization level. So definitely errors are generated. Error is simple, quantization level minus my original signal, right? So error in the case of quantization is given by quantized signal, that is xq of t. Xq of t is nothing but staircase signal minus x of t. X of t is my original signal. And this error is given by mod of s by 2. That means step size divided by 2 is my error. So error can be defined inside the quantization. It's quantized signal minus original signal. Step size is higher voltage minus lower voltage divided by q and 2 raised to n. Now one may ask that whether this step size is constant. Definitely not. This step size, we are having two types, that is uniform quantization and non-uniform quantization. As per the signal, if our staircase is generated, then it is non-uniform quantization. And staircase is stiff, and as that means staircase is constant, then it is considered to be uniform quantization. So inside the uniform quantization, step size is constant, and in non-uniform quantization, our step size is varying according to the input. Okay, then encoding. So this is how, just consider PCM exact process, analog signal to the input. Okay, block diagram, just remember, block diagram, we are having analog signal input, then sampling, then quantization, then encoding. Now, if we represent this in waveform form, again two-dimensional wave we are using, and always time representation on y-axis, on x-axis, sorry, y-axis we are having amplitude, on x-axis we are having time period. So consider this signal, again this signal is x of t, it is mathematical representation A, or we can say amplitude sine omega t. Then since it is pulse code modulation, we require pulse for a carrier. Then first process is sampling. Which sampling we are using? Always flat top sampling we are using, hence bubble starting for some time, again bubble is clock pulse generated for some time, then bubble, clock pulse generated for some time. Then Q here from this side, that is left hand side, you know that 3-bit representation. That means value of n is 3. Q is equal to 2 raised to n. That means 2 raised to 3. That means 8. It is ranging from 000 to 111. That means this entire slot consists of 8 different voltage levels. And where this signal cut, we will consider as our first pulse. Second signal, we will consider our second code. Third pulse, we are consider our third code. So where this signal cut, its equivalent voltage level, suppose this is 100, then we are representing 100. Here you will consider 101. So we are considering this pulse as 101. So this is how this entire signal represented in digital form with the help of this sampling, quantization, and encoding process. Okay, so these are 3 basic steps which we deals in PCM. So general conversion, now actual circuitry which we are using for PCM transmitter. So first we are having x of t as my input signal, then low pass filter, consider only low frequency signal. Okay, and rest of this low pass filter, that means low frequency should be passed through this filter. What about high pass, band pass? That remove, right? The low pass filter we can tune for the certain frequency ranges. Again, I'm giving same example. On the FM radio, we are having signal from, you know, that band. We are having 87 point something to 100 point something megahertz. So if you want to tune, suppose, for example, 500K signal, whether you will tune? No. So what is that tuner circuit will do? Tuner circuit will filter out the signal. So the same application we are using in low pass filter, we are setting a particular range. That means from this frequency to this frequency only allow. Other than that, we can remove the signal. Then this signal is passed through the sampling. S&H stands for sample and hold. Okay, in many of the books, S&H is mentioned, in many of the books, sampling is mentioned, but ideally it is sample and hold, because key we are opening for some time, then closing, opening and closing. In between then opening and closing, some time period is there, 2 microseconds, 3 microseconds. That means we are holding that signal for that particular time period, then and then only clock pulse is generated. Hence, always sampling and hold. So here you will see on the above, we are having sampling, that means chopping the signal. Then second position is quantizer, where we are deciding the various voltage levels. Third, where is the encoding, where we are using whatever n-bit representation we are using. If the 3-bit is there, then for each sample we are having 3-bit representation. If the value of n is 4, then for each sample we are having 4-bit representation. So this is how the encoding will generate a signal, and then with the help of parallel to serial converter, we are converting whatever bit stream in the parallel representation of signal. Whenever we are converting into serial, that means 3 times 0, 100, 101, 100. And this is how the serial bit stream generated, at which is the of our PC. Right? And all these blocks connected with some timer block. So the role of that timer block to generate this clock pulse. So this is how the basic PCM transmitter will work. Again, then process we are following at the PCM receiver. So bit stream input we are having. That means what? Sine signal as an input, 0101 representation as a PCM output. Then this PCM is provided to the PCM receiver. So what are the steps involved in PCM receiver? Exactly opposite to transmitter. So first we are having 0101 bit stream as an input, then it is provided to the regenerator, then it is provided to the serial to parallel converter. If you will see the block here, parallel to serial converter, then in the first step we are using serial to parallel converter. Then A to D converter, here we are using D to A converter. Then there also we are using S and H, here also we are using S and H. And in the PCM, first block is low pass filter, in the receiver side last block is low pass filter, and then we will get the analog signal. If you will see same diagram, this is what input to our receiver. Then the second block, quantization, where the representation of this, that means digital signal to analog conversion, will take place like this. And from this, we are getting our original signal. So whenever transmitter will do, from upside to downside, we have to follow. And whenever receiver will work from downside to upside, we have to see the same diagram. This is how represented PCM receiver. So up till now we have covered PCM transmitter, PCM receiver. What are the basic steps involved in PCM? Sampling, quantization, encoding. Laptop sampling generally use quantization. We are using Q is equal to 2 raised to n. Depend on the n, the quantization levels are there, and encoding is depend on this n. Suppose value of n is 2 bit, then for each sample we are having 2 bit. That means where the bit get differentiated here. If the value of n is 3, 3-bit representation. If the value of n is 4, 4-bit representation. So depend on the value of n, this bit representation gets generated. So I hope you understood the basic working of PCM. Now, what are the different formulas we are using as far as PCM is concerned? So first is quantization level. Always Q is equal to 2 raised to n. This quantization level. Second is sampling frequency. How much sampling frequency? Always sampling frequency is greater than twice of F max. Third, signaling rate is defined as capital N multiplied by F into S. So Fs stands for sampling frequency, and this N is nothing but the number of bits for the quantization level. Then most important parameter, that is the transmission bandwidth. So bandwidth calculation, always in the PCM you are getting question on these formulas only. Okay. So the transmission bandwidth is 1 by 2 R. What is R? Is nothing but N into Fs. Fs we can replace by twice of F max. So 1 by 2, 2 get cancel out. So N is equal to twice of F max is there. Right. Then step size, you know, VH minus VL divided by Q. Q is equal to what? 2 raised to N. Maximum error is mod of S by 2, where S is the step size. So why are we representing mod? If negative is there, step size is always positive. Hence, mod we are using. Then normalized signal power is always given by S square by 12. So signal to noise ratio, as far as particularly PCM is concerned, signal to noise ratio is signal power divided by noise power, right? Normalized signal, what do you mean by signal power divided by noise power? So always signal power given by S square by 12. And then we have to calculate the noise, whatever noise generated. So here we are considering two different noise, white Gaussian noise, or we can say a white noise or Gaussian noise. So there are various noises we are considering as far as mathematical analysis is concerned. But standard signal to noise ratio always 3 into P divided by x square max into 2 raised to 2n. So this P specifies the noise power. Signal power given by S square by 12, noise power we have to calculate, or in general numericals are given. At the end of this session we will solve some numericals, so in that case you will get a clear idea. X square max is nothing but entire amplitude of our signal, and 2 raised to 2n. This n representing the number of bits for the quantization level. In the case of dB, it is 4.8 plus 6n. And for sinusoidal input, it is given by 1.8 plus 6n. Definitely, there are various derivations are there. But what happened, in 2 hours, we will cover only some part. So just you have to remember this thing, and in the digital communication or either in FC, you have come across the derivation for this. So signal to noise ratio always is 4.8 plus 6n and 1.8 plus 6n. So these are the formulas related with the PCM. Now, the next technique is a differential PCM. So one may ask the question that why there is a different technique if PCM works better. You know that what happened depend on more here. Suppose the value of n is 3 bit input is there, value of n is 4 bit input are there, and number of n is 5 and 5 bit. That means for this signal only these many bits get generated, and the number of bits are more, bandwidth requirement is more, right? Suppose on the bike we are having the capacity of 2%. If 3% are riding, if 4% are riding, and if 5% are riding, what happened? You know that the bike will move slowly. So same thing will happen in communication. If number of bits are more, the communication, definitely communication will take place, but the speed of the communication get reduced. So what is the role of communication engineer? To increase the speed, right? For increasing speed, what is the alternate solution? Reduce the number of bits. That means instead of 5% riding on the bike, ride only 2%. You may use 2 bike or 3 bike. So this is what the solution, right? So here, whatever techniques we are advancing, that is PCM, DPCM, delta modulation, and advanced delta modulation, what basically we are reducing the encoding block size. If we are reducing the encoding block size, then what happens? Bandwidth requirement are lower. And if bandwidth requirement are lower, channel capacity requirement are also low. And therefore, we can provide service to the more number of users than less number of users. So basically, all this play is related with the number of user, number of subscriber. You always come across this term, that is Airtel having these many users, then Jio having these many users. So what is the play? The play is simple. Number of users should be more, but channel capacity remains same. For utilizing that channel capacity for number of subscribers, we require a modulation scheme. And in that case, the last portion, that encoding portion, should be low. That means instead of 4 bit, I will send only 1 bit. So this is how the technology will move ahead. Again, one may ask the question that, sir, analog communication will do a better thing. That means we are talking with each other with landline phone. Then why it is necessary to go for the digital modulation scheme? The answer is same. Landline can't the landline phone from one place to another place. So with the help of mobile, you can carry your mobile where wherever you are going from one place to another place. So this is how the need of technology takes place. And this is how the modulation we require to change from one point to another point. And another disadvantage with analog communication amplifier requirements are that for a certain distance, we require amplifier. In the digital case also, we require a regenerator circuits. But the distance, if you are calculating and if cost of the circuitry is calculating, then definitely the digital modulation scheme require lesser cost than the analog cost. Hence, we are moving ahead toward this wireless technology. So moving back to next point as far as exam is concerned, as far as syllabus is concerned, is our what the DPCM, that is different. So I will directly move the block diagram. So encoder block diagram. Again, three steps are common, that is sampling, quantization, encoding. Here, one additional circuitry will get added, that is prediction filter. I am giving directly one example. You know the working of sampling, you know the working of quantization, and you know the working of encoding. So I am representing here few points so you can understand what is being of the input to the signal. E of NTS, that is error. EQ of N is the output of quantizer. Then XQ of T is the quantizer signal. That XQ of T, you know the quantized signal, and X of T, original signal. What is error? What is error? Quantized signal. This is error X and T, X cap of T. That means quantized signal we are providing to the prediction filter, whatever output is there, of T. That means is coming from quantizer and prediction filter. So my error is original signal minus this and XQ of N, X cap of N minus EQ of N. You are not just, you can use any of the representation for this. I am giving you direct example what exactly happened inside the diagram. Okay. So I'm having these different voltage level 2.1, 2.2, 2.3, 2.6, 2.7 and 2.8. This signal is at input. Okay. So this first we are passing, then 2.2, then 2.3, then 2.6, 2.7, 2.8. So first signal will move is 2.1 with the sampling, then it is provided to the quantizer, and then this is provided to encoding. In that case, let us consider this step by step execution. So X cap of N, initially there is no value, initially it is 0 value, right? Error generated 2.1 minus 0, right? Here error is my X of N minus X cap of N, 2 point. EQ of N, that means quantization level, here 0.1 is there. So whenever we are doing the quantization, point will get removed. Just we are considering ceiling concept, or we can rounding off 2.1. Since 0.1 is there, we are considering only 2. If more than 0.5, that means thresholding is there, then we are increasing the bit. So since it is 2.1, quantization level is 2, and output of the final, that is XQ of T, is 2. These 2 is input for the next bit, right? Now 2.2 minus 2 is 0.2. Quantization since 0.2, 0, and the XQ is generated as 2. That means 2 minus this. So this is how we are generating a transmitter diagram, right? Suppose the first sending is 2, then why EQ of N we are considering? EQ of N is given to the encoding and DPCM is generated. So this EQ of N voltages we are considering for the transmitter of N. So this 2, 0, 0, 1, 0, 0. Now what is role of encoder? Whenever this 2 is providing to the encoder, suppose 2-bit input are there, that means 2-bit representation, how we are representing A and B. Suppose 2 raised to N is 2, 2 raised to 2, 4, There are four symbols: 0, 0, 0, 1, 1, 0, 1, 1. That means 0, 1, 2, 3, 4. For 2, we are definitely representing 1, 0. For 0, we are representing 0, 0, and 1, 0, 1. So this is how DPCM will generate an entire bit stream. Right. Here we are considering different voltage level. What happened in the PCM? We are having 3 bit, 4 bit, 5 bit information, but here we are having reducing that encoding blocks. Okay. As I already mentioned, our role is to reduce that encoding block bits only. So with the help of DPCM, we are definitely reducing these block only 2 bits, but definitely voltage level are very low. If the voltage levels are more, that means it is ranging from 2 to 16, then definitely the bit pattern are more. So for low voltage level, that means less than 5 voltage. Generally, as a EC engineer, we are dealing with max to max 12 volt, 15 volt, 20 volt, and most of the devices, as far as communication is concerned, works on the 5 volt. You know that battery will work. So that much voltage only we will require to run our devices. So I'm considering here low voltage. For low voltage, DPCM performs better. In which manner? In reducing bandwidth and reducing channel capacity. So you were saying exactly opposite processes we are doing. Just I will go with the. You will see signal is given to the decoder. Then it is provided to the encoder block, and with the help of low pass filter, we are getting our original signal. So here you will see that this is what original voltages we are passing, right? So from these we are getting output as 222,333. You will see that our original signal is 2.1, 2.2, 2.3. That means for first three signal, voltage level is 2. And for rest of the signal, 2.6, 2.8, 2.9, the voltage level is definitely 3. So what here, basically in DPCM we are doing, we are reducing the encoding blocks. So this is what the DPCM is concerned. Still, we are having 2-bit representation in the case of DPCM. In the case of PCM, depend on the value of n representing the data. Okay, I just want to ask you if you are Sumit sir. Hello. Hello, participants. Sumit sir, are you there? Hello. Hello. Okay. If anyone having any doubt, please ask me, or shall I continue? Amit Mandvi is there. Amit, any doubt? Till the time we have covered PCM, please use chat window. I think your voice is not audible to me. Oh, thank you. Then we will move forward with delta modulation. So what happened in PCM and DPCM? We are having number of bit representation in the output of PCM depend on this value of n. Suppose the value of n is 3, then encoding block having 3 bit. Suppose the value of n is 4, then 4 bit representation are there. Okay? Then in the DPCM, definitely we are having 2-bit representation for lower voltage level. Okay. Then we will move toward delta modulation. So what is the role of our reduce that encoding block size? For reducing that encoding block size, now what is minimum level? 0 and 1. That means 1-bit representation we will require so that the data size get reduced at the end of that encoding block. So what we are this delta modulation scheme, which will provide only 1-bit information after the encoding process. So it is quite simple working. Again, I am just explaining you with the help of a waveform. Consider this sine, and whenever this wave get cut with our quantized signal. So simple block arrangement is there. Sampling 1-bit quantizer in DPCM and DPCM, quantizer bit is not mentioned there. That is n bit. N bits mean 2 raised to 2, 2 raised to 3. So in the delta modulation scheme, we are having only 1-bit quantizer and output definitely only 1-bit representation. So here you will see that what exactly we are doing. We are what we can say, we are generating first 1-bit staircase with the help of quantization block, and then we are checking the variation, that means del. How we are checking? Current sample minus previous sample. We are comparing with this. If current sample is greater than my previous sample, then 1 is sent. And if my current sample is less than previous sample, then 0 is sent. That means only 1010 we are sending with the help of this contact. So ultimately what happened? We are sending only either positive value, negative value, positive value, negative value, positive value, negative value. That means here we will send 11000. Instead of 000, 111, 000, we are sending only 1-bit information here. Hence, the encoding block will get reduced. It will result in reducing bandwidth, and it will result in reducing channel capacity. So all these are related with the number of bits we are sending. Again, some errors are generated in delta modulation, that are quantization error and slope overload. I think in FC you have studied in detail. Then and final solution, the quantizer delta modulation, we have already discussed the quantizer two types, that is uniform, non-uniform. In generally PCM, DPCM, delta modulation having uniform quantization, and DPCM, sorry, the adaptive delta modulation, we are having the non-uniform quantization. That means step size is not constant. Step size is changing according to input. Here you will see a clear-cut difference. If a constant step size is there, then what happens? This is my original signal, right? Here I have mentioned that original signal. This original signal, and if the step size is constant, then there is a lot of difference between my original wave and contact signal. So what is alternate solution? The solution is varying step size according to the input. So this is what non-uniform quantization which we are using in adaptive delta modulation. Again, concept is same. It will get compared with previous sample, right? Here in this sample compared with this 0 or 1 is sending. This sample is compared with this 0 or 1 is sending. If the same sample is there, then 1 is sending or 0 is sending. So 1-bit information we are sending per sample as far as delta modulation is concerned. But since if we are using the non-uniform quantization, then it will provide a better result. Hence, nowadays also we are using adaptive delta modulation for reducing data. This is how we have covered PCM, DPCM, then delta modulation and adaptive delta modulation. So what happened in the pulse code modulation? More number of bits are there. Then we are reducing number of bits in DPCM. We are still reducing bit. That means suppose in the case of PCM, we are having more than 2 bit, 3 bit, 4 bit. In the case of per sample, we are having 2-bit, 3-bit, 4-bit, 5-bit kind of thing. In the case of DPCM, we are having 2 bits per sample. In the case of delta modulation, we are having 1 bits per sample, but we are using the uniform quantization level. That means there is a huge quantization error if we are using the delta modulation scheme. For reducing that quantization error, we are using adaptive delta modulation, which will result in 1 bit per sample with exact value. That means reducing quantization error and sending appropriate information. We are using the adaptive delta modulation. So this is how we are generating signals with the help of adaptive delta modulation. So basically what we are doing, we are converting our sine signal into digital signal with the help of these different modulation schemes are there, right? Next, we will having the concept regarding shift. I'm asking if you are having any doubt regarding this PCM, DPCM, delta modulation, and adaptive delta modulation, please ask me. As far as gate is concerned, PCM is most important thing because most of the numericals are covered in the form of PCM. In the last section of my discussion, I will take some numericals from gate point of view. But still, if you are having any conceptual doubts, you can ask me. Sumit sir, are you there? Hello. Hello, Sumit sir. Yes, please attendees, please respond if you are having any doubt or still I continue. Use your chat windows. Are you getting the concept of complete? Madhuri, Pooja, Tanushri, please use your chat box.
Hello, sir.
Yes, yes. Hello, Sumit
Sir.
sir.
Yes, sir.
Yes, please, anyone having any doubts, sir? I have covered PCM, delta modulation, adaptive delta modulation. But then, so whatever covered we have till the time, get point of view, PCM is important. Right? So next we are moving toward techniques. So one may ask the question why? If it is fine, we are having analog communication. You are saying that it is having a problem, amplifier are needed at a certain distance. Then we are came across digital modulation scheme. In digital modulation scheme also, you are saying PCM having more number of bits, then DPCM having lesser number of bits, and then adaptive delta modulation is base scheme. Then it is fine. We are using adaptive delta modulation scheme for communication purpose and we are doing the communication. Then why we are going for the next technique and the next method, that is shifting technique. See what happened. So we always require a transition from analog conversion to digital conversion. For example, just I am giving you one example. Suppose you are watching live match. So what happened? The match is recorded on the video. That means in analog form. Then they are sending that information with the help of either satellite or optical fiber. That means in the channel we are having digital data or analog data. Again, that data we on the TV, whenever you are observing on the TV or mobile, it will convert it into analog form. So there is always a transition from analog data to digital data to analog data. So for this transition, we are having various techniques. So that is what the ultimate solution. If analog to analog communication, we are having our continuous wave modulation. If analog to digital conversion, we are having digital modulation scheme. When digital to analog conversion is there, that means digital input converted into analog form. Best example is your set-top box. On the set-top box, backside you are having one wire, that is optical cable, which will carry digital information, right? And that digital information converted into analog form whenever you are observing on the TV. So for this conversion, that means digital to analog conversion, we require a shift keying technique, right? So the first technique and scheme, that is continuous wave, which is used in FM, AM in our low range communication. We can suppose we want to communicate within Nagpur. In that case, we are using FM or AM. And whenever digital data conversion takes place, we are using our digital modulation schemes, right? Like PCM, delta modulation, and all these two. And whenever we require more long distance communication, that means digital to analog conversion, and again analog to digital conversion, in that case, we are using the shift keying. So we are starting with some called bitrate and baud rate. So bitrate stands for number of bits per second and baud rate stands for number of symbols per second. Okay, please see carefully what is basic difference in definition. Okay, what they are always asking about what should be the bitrate, what should be the baud rate. So you can't confuse. Here I am having two examples where you will understand what exactly basic difference between bitrate and baud rate. So bitrate is number of bits per second, 8 bit, 16 bit, 32 bit, and number of symbols per second. Okay, suppose 2 bits, 4 symbols are there, 2 raised to 2 means 4 symbols, 0001, 1011. 2 raised to 3, that means 3 bits, but how many symbols? 8 symbols are there, ranging from 000 to 111. 4 bits, but 16 symbols are there, ranging from 4 times 0 to 4 times 1. So this is what relationship between bits and bit rate is given by capital R, number of bits per second. I'm getting some. Hello. Okay. Then number of symbols, and this is how Sumit sir. Hello. Hello.
हाँ आकाश मी तुला नाही का
So
फॉर्म भरलाय ना ऍडमिशनचा फॉर्म भरलाय मी तुला पीडीएफ पाठवली
hello.
कर सगळं बरोबर आहे का काही करेक्शन असेल तर सांग मला पटकन चेक कर हा पीडीएफ पाठवली आहे
Hello Sumit sir, please mute your mic. Hello. 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 Sumit sir. Okay. So this is what relationship between bit rate and baud rate. So bit rate is given by capital R and baud rate is given by small r. So small r is equal to capital R divided by n. Okay, baud rate is equal to ratio of bit rate divided by number of bits per symbol. Okay. So the total number of symbols is it's same. Q is equal to 2 raised to n. L is equal to 2 raised to n. So here I am having differentiated between bitrate and baud rate. So consider an analog signal carries 4 bits per symbol. That means value of small n is 4 bits per symbol. Element if 1000 signal are same. That means small r, right? Number of element related to the baud rate. So baud rate is 1000. So there is a question, find the bit rate and total number of symbols. So what is bit rate? Bit rate is equal to, use this formula, small r is equal to r by n. Bit rate is capital R, small r multiplied by n. Here your answer is 4 kbps. So bit rate is 4 kbps and baud rate is 1 kbps, right? So this is how the question will frame. So there is a difference between bit rate and baud rate. From this, you can understood it. And then the number of symbol is simple. Q is equal to 2 raised to n, L is equal to 2 raised to n. It's 16 elements. Similarly, in second numerical also, please read out. An analog has a bit rate, that means capital R value is 8000. Then baud rate, that is small r, we are having the 1000. We need to calculate the number of symbol and total length. So the formula is same. Small r is equal to r by n, from which we are getting the n, that is bits per symbol, and then length is 2 raised to n, that is 256. So this is how there is a differentiation bit rate, baud rate. Okay. Then we will go for, as I already mentioned, there are three attributes which we can play with the signal, that is we are having amplitude, we are having frequency, and we are having particularly phase. So according to that, shift keying technique are there, that is amplitude shift keying, frequency shift keying, and phase shift keying. Before moving forward, okay, shift keying is used in modem. Modem is used in our TV box or CPU box. In CPU for accessing internet, we are using, and for TV on set-top box, this technology we are using. Again, nowadays we are using QAM, which is again a combination of ASK and phase modulation for TV transmission purpose. If you are auto-tuning your set-top box, then it is mentioned that 256 QAM. QAM stands for quadrature amplitude multiplexing, in which the concept of ASK and PSK gets clubbed. So how they are clubbed in that concept, just we will come across. So we will start with this ASK. So in amplitude shift keying, see what happened. So again, as I already mentioned, shift keying, digital input, convert it into analog signal. That means digital to analog conversion takes place. In PCM, what happened? Analog to digital conversion takes place, right? In digital modulation scheme, whether it is PCM, whether it is DPCM, whether it is delta, whether it is Z up to delta, what happened? Analog to digital conversion, right? In the case of shift keying technique, digital to analog conversion takes place, right? So input again is digital signal and convert it into digit, right? So here one basic diagram is there. The input signal is digital. So M of T represents the message signal, which is in digital signal. Here you will see 0. Then carrier is analog, since digital to analog conversion takes place. So carrier is my analog signal. And what is output ultimate? Output is analog signal, right? So what happened in amplitude shifting, the concept says that whenever data, input data is 1, then carrier will send. If input data is 0, no carrier will send. It's very simple, right? Consider each sample. So this is sample for 0, this is sample for 1, again 0, again 1. The ASK concept says that amplitude shift concept says that whenever data is 1, that means input data is 1, send carrier information. If input data is 0, did not to send the information. So what we can do? We can just here add multiplier. So what happened with the multiplier? In each sample, the data will get multiplied with each other, right? Consider first sample. My voltage level is 0. Carrier is having this. 0 multiplied by something, always 0, right? 1 multiply with this carrier signal will send some signal. Again, 0 multiplied by this, 0. 1 multiplied by carrier signal is output. So this is how our ASK output generated. It is also known as binary ASK. See, we are having all these techniques ASK, FSK, PSK with some name, that is binary ASK, quadrature ASK, octa ASK. So whenever we are dealing with only 1 bits per sample, 1 bit per sample, then it is considered to be binary. Whenever we are dealing with 2 bit per sample, 2 bits per sample, in that case we are considering quadra. Why? 1 bit, 2 raised to 1, 2 combination only 0 and 1, hence it is binary. If 2 bits are there per sample, 2 raised to 2, 4 samples, 4 symbols are there. 4 symbols means quadra. 3 bits are there, we are having octa. So depend on how much bits we are dealing with per sample, depend on this nomenclature is given. As far as gate is concerned, we are dealing with only binary. That means one bit input. 1 bit inputs mean two symbols are there, either 0 or 1. According to that, as nomenclature is given. So first is our binary ASK. So what happened in the binary ASK? It is simple. Having some message bit as input. What is input in the case of ASK? Digital signal. Then we are having carrier signal. In the carrier signal, again we are having sine wave kind of thing, because carrier having the higher frequency, and both get multiplied, which will result in the output. Okay. So here you will see we are having 0 1 0 1 0 1 0 1 as a input, right? Then it will get multiplied by the carrier signal. For each sample, we will multiply this. For 0 multiply by this, we will get 0. 1 multiply by this, we will get some signal. 0 multiply by this, we will get some, we are not getting the signal. So concept says that whenever data 1 is there, input data 1 is there, send carrier signal. Otherwise, do not send carrier signal. So simple, we are just multiplying and generating this ASK signal. So the mathematical calculation bandwidth is given by 1 plus D multiplied by R divided by N. Now what is small r? You know, baud rate. Capital R, you know, data rate. Then N, number of bits required for sample. T is the factor for modulation, and it is always ranging from 0 to 1. From this formula, we can calculate the bandwidth of ASK signal. So when demodulation of ASK takes place, definitely there are 2 types. The first is the synchronous, second one is the non-synchronous. It is quite simple. In non-synchronous, we are dealing with the envelope kind of thing. You know that AM, we are having envelope and we are having the signal. So whenever we are dealing with the envelope kind of detection, that means only waveform we require. In that case, we are using the non-synchronous demodulation. Otherwise, we are using our simple arrangement of signal and filter. So depend on the application. Generally, we are using our coherent detection because it is cheaper one. In non-coherent, what happens? Envelope detection takes place, and then additional circuitry we will require at the end of demodulation. So coherent is cheaper, non-coherent is quite expensive as compared to synchronous. So generally we are using the synchronous detection as far as ASK is concerned. There is one example I am giving you. The consider bandwidth is given, varies from 200 to 300 kilohertz. what are the carrier frequency bit rate if we are having BASK with D equal to 1. So we know the formula 1 plus D multiplied by R. So small r is equal to capital R by N. Just put the value, get the result. We are having the various parameters with the help of formula. So this kind of question may ask in the GATE exam for ASH concern. Next is FSK. So what happen in ASK? Whenever data is zero, it will get multiplied by carrier signal. If zero multiplied by something, zero is there. One multiplied by something, carrier signal is there. So this is how signals are generated. So just a 2 seconds, I require a break. I'm just drinking some water for 2 minutes. Okay. Now the concept of FSK. What happened in FSK? FSK stands for frequency shift keying. So in frequency shift keying, we are having two different frequencies. Okay. One frequency will get multiplied by 0th signal. That means whenever voltage level is zero, we are multiplying that frequency with zero signal. Or we may say that it is low frequency. And whenever data 1 is there, then high frequency. So how many frequencies we will require here? We will require here two different frequencies. That is, one is low frequency. Okay. So this one, whenever data 1 is there, it will get multiplied by a higher frequency. And whenever data 0 is there, it will get multiplied by lower frequency, right? So the multiplication of higher frequency and lower frequency depend on what is the input. If the input is 1, it will get multiplied by higher frequency. If input is 0, it will get multiplied by lower frequency. So this is how our frequency shifting signal will get generated. So let us begin from block diagram also. You will understand that how work. In this it's simple. M0 of t. So I am considering here 0 bit multiplied by low frequency and 1 bit multiplied by high frequency, which will get a output. Start with this. We are having 1 multiplied by higher frequency. So here higher frequency component 0 multiplied by low frequency component 1 multiplied by high frequency component and 0 multiplied by low frequency component. So you will see here the FSK diagram. So what is basic difference between FSK and ASK? You will see here simple. In ASK, whenever data is 0, no frequency component is there. We are having frequency component only for 1 bit. That means whenever data, whether in the case of FSK, we are having both frequency component, but higher frequency component whenever data 1 is there and lower frequency component whenever data 0 is there, right? So bandwidth is given by 2 multiplied by 1 plus dr plus 2 times del f. What is del f? Is change in frequency. So same numerical you may solve with the help of this. Demodulation is again two types, that is coherent and non-coherent. In coherent, what happened? The arrangement of low pass filter. It is basic concept that whatever carrier frequency we are using at the transmitter, same carrier frequency we are using at the receiver, same signal. That means suppose cos signal is this, cos 10 we are using at transmitter, same cos 10 we are using at the receiver, and then pass the signal with the low pass filter and generate our original signal. In the case of non-coherent, we are having the arrangement of band pass filter plus and envelope detector kind of thing. So as I already mentioned, non-coherent detection is expensive since envelope detection is there. Again, one standard numerical as far as bandwidth is concerned. So if user want to send data 3 bit, that means small n value is 3 bit at a time, and bit rate you know, it is given by capital R, that is 3 Mbps, and the carrier frequency, that is FC, is 10 megahertz. Calculate number of levels, baud rate and bandwidth. So number of level we can calculate L is equal to 2 raised to n. Since the small n value is given is 3, 2 raised to 3 is equal to 8. Then small r, that means baud rate is given by capital R divided by n. The speed is 1 Mbps and its bandwidth is given by L into R, that is 8 Mbps or 8 megahertz. So this is how you can calculate the bandwidth with the help of given data. Definitely there is a derivation. If you want to study that entire derivation for the bandwidth, you may use any of the book, but as far as gate is concerned, you require only formula for solving the numericals, right? Then the major concept of DPSK. We are having 3 attributes: amplitude, frequency, phase. We are dealing with the amplitude. In amplitude shifting, what happens? If data 1 is there, it will get multiplied by carrier wave and signal will generated. If data is 0, no, that means no waveform is there in the ASK modulation. In the case of FSK modulation, whenever we are having 0 and 1 data, 0 get multiplied by low frequency, 1 get multiplied by high frequency, and the final output will get generated. In the phase shift, again, we are having only 2 bits, that is 0 and 1. Whenever data changes from 0 to 1 or 1 to 0, phase shift get occurred. So what do you mean by phase shift? Phase shift means starting position of a signal, right? If sine wave is there, we are generally starting with the initial position. That means 0th position, right? And whenever data starting for direction than the zero and minus lower direction than the zero. So basically phase difference is origin of the signal where we are starting. Just I will say what do you mean by origin of a signal. So this is what origin of a signal. Consider this sample. This signal will start in negative direction starting from zero. That means 0 degree. If it is 180-degree phase shifted, that means mirror image of that. That means signal will start from here and end will here. You will see the peak difference. Here the first positive peak, negative peak, then negative peak, then positive peak. So this is how the phase gets shifted. Where we will see phase shift we will see at the starting of the symbol. Right? So here 1 to 0, 0 to 1. Whenever data will change, phase shift will occur. Right. Then diagram, it's simple. We are having message signal, always message signal either in 1010 form. Then we are having carrier signal. They will get multiplied and depend on the phase we are generating our phase shifted signal. Since here low pass filter we are using, it is coherent detection. Okay. So there is a question, what is cheaper detection mechanism? Coherent, non-coherent, both, none of the above. So always keep in mind, coherent detection is cheaper one because we are using same carrier frequencies as that transmitter. But in the non-coherent, we are using the envelope detector thing. So additional circuitry required, cost of the circuitry will become higher side. Hence, the non-coherent detection is the expensive than the coherent detection. Okay. So next point is dealing with this, particularly the ASK technique, right? So we are having input signal and then this PSK signal, how it is generated. Okay. So before moving to how these signal are generated, I just want to say you something. Since it is binary, the entire phase shift we are considering as 360-degree. So 360-degree divided by 2, that means 180-degree. That means each phase shift is of 180-degree. That means in one symbol there is no phase shift and another symbol there is a 180-degree phase shift. So while drawing the diagram, I am considering whenever data 1 is there, there is no phase shift. That means whatever carrier signal we will consider as it is. And if 0 data is there, 180 phase shift is occur, or vice versa. You can take, just it is a representation. Okay. So consider my input data 1010. Okay, carrier signal, one cycle per sample. So what I am considering, whenever data 1 is there, as it is carrier wave. So what data 1, we are having carrier wave as it is. But whenever data 0, 180-degree phase shift. 180-degree phase shift means mirror image of this. Okay, I am not going into detailed phase and QPS. You have already studied. We are not required as far as gate is concerned. Okay, just I am representing this because of that pictorial form. You can understand where it will get changing. Okay, so here you will see 180-degree phase shift of what? This, and mirror image. So here you will see it is starting from 0, positive side, negative side. Then mirror image means negative side, positive side. Here you will get phase shift. Again, whenever data changing from 0 to 1, here 1 is, that means as it is data, and 0 mirror image there. So this is how these mirror images are generated, and from that are getting the phase shift. So this phase shift of 180-degree. So till the time what we have covered ASK, PSK and FSK. So what happened in ASK? Whenever data 0 is there, no signal is generated. Whenever data 1 is there, carrier data is generated. Then in the case of frequency shifting, two frequencies we are using, either high frequency or low frequency. If data 0 is there, data will get multiplied by lower frequency. If data 1 is there, it will get multiplied by high frequency. And PSK, phase shift key. What happens whenever data changing from 1 to 0, 0 to 1, phase shift of 180-degree occurs. Okay, all these techniques we are considering only for one bit. That means two symbols, 0 and 1. Again, PSK, we are having QPSK, that means 2 bits per symbol. That means per sample, if we are considering 2 bit, then it is QPSK. If we are considering 3 bit, then it is OQPSK. That means octa QPSK techniques are there. There is a lot of scope and development in this particular PSK kind of thing, shifting technique. So that because nowadays we are using modern kind of circuitry, so always we require modulation schemes, design of modulation scheme as far as communication is concerned. And nowadays we are using 4G, in which we are using MSK technique, 0.9 GMSK technique we are using as a modulation scheme in 4G technique, which is belonging to the FSK. Okay. So frequency shifting technique we are using in our mobile communication, while ASK and PSK technique combine QAM, quadrature amplitude multiplexing, which is used in our TV transmission. As I already mentioned, just you can go for manual tuning, not automatic tuning. Then below one line is coming 256 QAM, 64 QAM, 128 QAM. So that QAM represents this quadrature amplitude modulation, which is the combination of amplitude shifting along with the phase shifting. So the block diagram is having, we are having again digital input data provided to the serial to parallel converter, then it is given to D2A converter, and then it is given to the product modulator, and finally with the help of multiplication with some frequency, a waveform is generated. So final output we are having x1 of t multiplied by cos frequency, x2 of t multiplied by sin frequency, and then at the decoder side, exactly opposite process of modulation. Same product modulator we are using, since phase shift of 90-degree passing to different signal. And whenever data we have to represent, see here we will get 16-bit QAM. That means in each quadrant we are having 4 different data representation. In 64, then each quadrant we are having 16 QAM. So this is how this QAM will work. Okay. The next concept is related with the match filter. Okay, what do you mean by match filter? Okay, whenever we are using different modulation schemes, ASK, PSK, FSK, demodulation, we require a detection at the receiver side. So this is what the typical example of match filter. Consider two signals, S1 of t, S2 of t. We are having at the receiver with the help of noise. So what is role of filter? Remove that noise and pass this signal. Then the sample energy of this signal at the output we are given by S0 of t and S01 of t and S0 of t. So it's as far as exam is concerned, what is important? We require its signal to noise ratio and error probability. So signal to noise ratio is given by 8E divided by efficiency. Efficiency is output by input, and E is the energy of a signal. So signal to noise ratio as far as match filter is concerned is 8E divided by efficiency. Right? What is efficiency? Efficiency output by input, and error probability is given by 1 by 2 ERFC under root E by N. Again, E is the energy of a signal, eta is the efficiency output by input. So these two formula you have to keep in mind while solving the numericals on match filter kind of thing. Next is, here is some comparison given for various PSK technique. You will clearly see here we are interested only in binary PSK and binary FSK. So DPSK, QPSK, MRFSK and MSK you need not to watch. So bits per you will see here. So in the case of BPSK1, in the case of BFSK also one. Bandwidth twice of FB, 4 times of FB. And symbol duration here TB, same as TB. So you will see here, there is a huge bandwidth difference between BPSK and BFSK. That means bandwidth requirement are more in BFSK. Why? It is simple. Since we are using two carrier frequency, bandwidth get more, and here we are using only one carrier frequency. Our bandwidth requirements are less. So as far as communication is concerned, we are using PSK and FSK technique in most of the cases whenever communication will happen. Now, moving back to third parameter, that is Hamming distance. What do you mean by Hamming distance? Hamming distance is number of bit change between two different bits is nothing but your Hamming distance. Okay, where this will come into picture, Hamming distance. Okay, all these distances are used in retrieval purpose or similarity measurement is concerned. Just I am giving you one example. Consider a system where we are having number of images, right? And you want to see a particular image from that image database, right? Just like in the Google you are typing, suppose Lotus you are typing, and whenever you are moving to the images tab, what are the Lotus images or tagged images Lotus that will displayed on your screen. So what happened whenever we are typing Lotus and click on the enter, the distance will be measured between that Lotus word and whatever the database we are having. That is considered to be indexing kind of thing. So what happened? That Lotus word having one point, one keyword, and that means one feature. Suppose one point is feature, and whatever database is indexed in the Google, it is ranging from 1 to 10. So whenever you are using keyword, then distance will measure. Suppose 1 and 1 same, then images is displayed. 1 and 1.1 same, images are displayed. 1 and 1.2 is same, images are displayed. So the calculation of these differences with the help of various distance parameters. So inside the communication block, we are having Hamming distances. Suppose X symbol having 101 and Y symbol is 110. So what is Hamming distance? Hamming distance is number of bit change. So let us consider first bit 1 and 1, no bit change. Second bit here 0 to 1, that means number 1 bit change, and last bit 1 to 0. So 2 bit change is there. That means only first position there is no bit change. In second and third position there is a bit change. Hence Hamming distance for these 2 bit is 2. Okay. Where the Hamming distance will come into picture, we will see some numerical. So this is what a typical encoder decoder diagram whenever we are actually doing the communication. As I already mentioned, input is provided to the transmitter. So inside the transmitter, there are 3 blocks: source encoder, channel encoder, modulation. Then it is passed to the transmitter. So input message bit, consider it is passed to the channel coder model, and here noise will get added and then transmit the signal. So at the receiver, the noise plus original signal is input provided to the demodulator, then channel decoder, and we are getting the output as a massive. So mathematical representation, code rate, you know that code rate is equal to capital K divided by N, where K is the number of bits appended. So here I am just giving you for mathematical. Let us say K is the message bit, and it is encoded bit 1 block sum bits added by encoder. So total encoded block will become n comma k, where k is your message bit and n is bit. So this k is the number of message bit and n is the total encoded block, right? Then channel data rate, you know, n by k multiplied by r. So Hamming distance is difference between two x and y. Here you will see 101, 110. First bit as it is, second 0 to 1, and third 1 to 0. So here it changes 2 bit, right? And there is one formula is related with error correction and error detection in as per as our syllabus is concerned. So this error correction is given by minimum distance is s plus 1. So from this having distance, we are calculating minimum distance, and from that this error detection. So s represents error detection and this t represents the error detection. So this minimum distance we are calculating with the help of Hamming distance, and from that we can calculate error correction and detection with code efficiency. The code efficiency is always given by eta, that is k by n. And one more parameter, weight of a code. Whenever digital communication is there, weight of a code means number of one represented in entire code. So let us consider this. Here we are having 1, 2, 3, 4, 5, 1. Hence weight of this code will become 5. Right? So let us consider this example. So we are having some parity kind of matrix, having some message bit and some parity bit. From that we have to calculate minimum distance, error corrected, error detected, and Hamming encoder. So let us consider this block where suppose this is message bit. Okay, then these are the code vector which we are generated with the help of coder, and then we have to calculate weight of a code. So right, so from these first you will see all 0, that means no single data 1, hence weight of a code is 0. In the second parameter here 3 number of 1, hence we are writing 3. Then here 3 number of ones, that is weight of a code, and from that minimum distance. In all these things 0, 3, 3, 4, 3, 4, the minimum value of weight is 3. So the minimum weight of this code will become 3. Then how many error detected? So minimum distance is 3. S is number of error detected plus 1. So this 3 minus 1 will become 2. These many error gets detected, right? And minimum distance 2t plus 1, that means minimum distance we are having 3, 2t plus 1, 3 minus 1, 2. 2 by 2 will become 1. That means how many error corrected? 1 error get corrected. So with the help of this kind of codes, we can calculate how many error corrected and how many errors are detected. So these are some examples related with error calculation whenever we are doing the analysis as far as data involved or data sets are given, right? Then here at the end we will solve some numericals as far as PCM is concerned. So before solving some numerical, just I want to brief you whatever till the time we have seen, and some portion related to the error detection and error correction. So up till now we have seen some formulas related with the error correction and error detection. Okay. Inside the channel encoder, if you will see this diagram, you know that in the transmitter, what we are having, we are having 3 different blocks: source encoder, channel encoder, modulation scheme, and then transmitter. This modulation scheme dealing with the AM, FM, PCM delta modulation, ASK, PSK, FSK. Then before that, we are having channel encoder. So this channel encoder, we are having convolution kind of coding is there. With the help of that convolution coding decoding, we can calculate how many error corrected and detected. So this is what typical example we have taken. How many error corrected and detected with the help of these number of message bits. Suppose we are having 4 message bit and 3 code vectors. From that 2 error detected, 1 error corrected, and this is what the Hamming encoder. Okay, how to draw? Definitely there is a need not to draw Hamming encoder, but if there is a similar question of this diagram, what should be the output? In that case, number of message bit, number of code vector, and they are connected with each other by this symbol. Okay. Then in the channel encoder, what happened? Generally, we are using convolution kind of coding. Okay. Again, we are having state table. According to state, output is generated. So here is a simple convolution encoder. We are having two output, V1 and V2. A message, that means we are having 3-bit message, M1, M2 and M1, M2 for V2. So this is my current state. Here you will see the first two point we are having 0, 0, then 0, 1, 1, 0, 1, 1. That means here are 4 different stages. For 0, 0, we are considering A stage. For 0, 1, we are considering B stage. For 1, 0, we are considering C stage. And for 1, 1, we are considering D stage. It is 1-bit shift register. Whenever data will input and 1-bit shift occurs, we are getting our next. So this A stage, whenever M value is 0, moving to A. That means A stage, whenever data is 0, moving to A. And A stage, whenever data, that means last bit is 1, moving to B stage. Similarly, B stage, whenever last bit is 0, moving to the C stage, and same B stage, whenever last digit is 1, moving to the D stage, right? Similarly, C stage, whenever the M bit is 0, moving to the A state, C D state, and D state, whenever data is 0, moving to C, and D, when data is 1. And how this table V1 will be generated? It is simple. Just put the value M, M1, M2. So first case, 0, 0, XORing 0, we will get 0, right? Similarly, this table will get generated. Okay. So these are the 3-bit input. That means number of stages are 8 and having this diagram. Okay. This is how convolution coding generated. Now, what is our concern? Why we'll study this? How the error are eliminated. Let us consider this is what data we are received at the receiver, right? So suppose this data, right? And I will say that whenever 1 is there, there is an error. And I will require only all zeros. Then and then only my data is correct. Okay, in digital communication, data error means what? 1-bit error. Instead of 1, if you are sending 0, and if instead of 0, if you are sending 1, there is an error. Hey, suppose I am receiving this data at the receiver, and I am saying that whenever 0 is there, only correct data, and whenever 1 is there, there is a error. So what we are doing, we are using application of Viterbi decoding algorithm. So what happened? Let us consider this part. Right. So by considering this part, what happened? All error get eliminated. Right. In place of 1, 0 is there. In place of 1, 0 is there. In place of 1, 0. And in place of 1, 1, 0 is there. That means with the help of application of Viterbi decoding, we can remove the error which is used in the transmitter. So again, I'm going back to same diagram. Noise added. What happened? The data will get corrupted, and that corrupted data we will remove here, right? Here noise get added, and this noise signal from the channel. That means instead of 0, 0, we are getting 1, 1. So what is the role of decoder? To remove that particularly noise with the help of algorithm. So one of the algorithm is algorithm. From here you will clearly see that if I'm sending a wrong data, then with the help of application of Viterbi algorithm, right? Instead of 1, 1, suppose this is error, 0, 0 I am receiving. That means at the end of decoding, I am getting my original signal. So this is one of the applications where we are using Viterbi algorithm for decoding the data. Similar kind of thing, numerical is there. Here you will see with the help of same application, suppose my received data is 0, 1, 0, 0, 1, 0, 0, 0, and there are 2 errors, that is second and fifth position. With the help of channel decoding algorithm, we can remove the error. Which is channel decoding algorithm, which is similar to this. So this is what my transmitted data, this is what my received data. That means I am eliminating the error with the help of channel decoding algorithm. Again, there are various channel decoding algorithm. They are dealing with the information theory and coding. Now, moving back to our PCM formula so that it will quite clear you to solve the numerical. So just I'm roughly briefing what are the formulas we are using in PCM. So my first formula is Q is equal to 2 raised to N. What is Q? Quantization level. What is N? N is the number of bits. Then Fs is greater than equal to twice of Fmax. What is Fs? Sampling frequency. Fmax is the whatever symbols we are using with some frequency, out of which the maximum frequency, suppose I am having three symbols 10, 20, 30, the maximum value is 30 and sampling frequency is 60. Then data rate is given by capital N. This N is similar to this N, that means number of bits multiplied by sampling frequency. Then transmission bandwidth is given by 1 by 2R. Just putting the values different, we can get this formula. Then step size is given by VL minus VL divided by Q. Maximum error is given by mod of S by 2. Why mod? If negative negation value is there or negative value is there, you have to keep error in positive symbol. Normalized signal power always given by S square divided by 12. What is your step size? And signal to noise ratio, we are having standard formula for dB 4.8 plus 6N. For sinusoidal input 1.8 plus 6N, and if the noise power is given, this P represents the noise power, this X max represents the voltage levels, and this N represents the number of bits. So we will take few these so that you will get what exactly you have to calculate in the case of examination. So let us consider our first example. A TV signal with bandwidth 4.2 megahertz. So I have written here also what is input data. Just you will see that. So any of the parameter they can ask in the exam. So my TV signal having bandwidth of 4.2 megahertz. That means my Fmax is 4.2 megahertz. Transmitted using PCM since pills called modulation. The number of quantization level is 512. That means what is given? Q is given. That is 512. Calculate code word length. That means what we have to calculate first? We have to calculate N. Second, we have to calculate transmission bandwidth. Third, we have to calculate bit rate. And fourth, we have to calculate signal to noise ratio. So what is given? So the first, what we have to calculate of N, we have. So formula Q is equal to 2 raised to N. Just put the value 512 2 raised to N. Then make a log, take a log, and then we will get value of N is 9 bits. That means whenever 9 bits are there, how many quantization level? 512 quantization level are there. Okay, in exam, vice versa question is also there. They may give a 9-bit information, find out quantization level, just 2 raised to N, 512. So there are a lot of possibility to ask any with the help of formula. You can ask this parameter, vice versa. So I'm clubbing all these parameters and so that you will get a clear-cut idea what exactly you have to calculate. Right. Then next is transmission bandwidth. So we are having various formula for transmission bandwidth, right? It is given by 1 by 2R. Right. If we are keeping the value in this numerical, what we are having, the number of bit N and Fmax 4.2. So just I'm putting the value, I am having the result at 37.8 megahertz. Then data rate is given by N into Fs. Whether Fs is given, sampling frequency is given, no. But you know what is sampling frequency? Twice of Fmax. So since here we are having F 4.2, then we are just putting the values and getting the result. That is data rate is 75.6 Mbps. That is megabits per second. And signal to noise ratio, how to calculate? 4.8 plus 6N. Since it is not given sinusoidal input, we are considering here 4.8 plus 6N as a formula for calculating signal to noise ratio. Similar. Next numerical. So all these numericals are club of 1 mark and 2 mark question which are asked in the, and definitely you have to use some mathematical expression for calculating this value. So the second, again, here I'm mentioning whatever data is given. Okay. So bandwidth of the signal input to the PCM is restricted to 4 kilohertz. That means maximum FM is 4 kilohertz. Then input varies from minus 3.8 to 3.8. Okay, voltage level are given. You know one formula, signal to noise ratio 3p divided by x square max. So x max is 3.8 here, right? Then average power 3 into p. So p is given, that is noise power is given is 30 milliwatt. Then what we have to calculate, the required signal to noise ratio is 20 dB. That means value of dB is given. And then we have to calculate number of bit per symbol, and output of 30 such PCM coders are time multiplexed when minimum required transmit. Okay. Basically, we have to calculate and VT from given data. So signal to noise ratio in dB, you know that 4.8 plus 6n, it is given as 20 dB. From that, we can calculate signal to noise value as 100. We are having formula for noise power 3 into P divided by x square max. Here P is the noise power, x square max is the amplitude level, and this N is the number of bit is there. So by putting all the value, we are getting the 7-bit information, right? And this 7-bit information is used for 30 PCM bit coder, right? So for that purpose, we require a bandwidth of 840 kilohertz. Just if you will see here, they are asking about directly bandwidth. So what first step you have to calculate? And by putting these values in this, you have to calculate your bandwidth. So most of the time in the gate, bandwidth calculation numericals are there. Then the third numerical, I will just brief out. So what is given and what you need to calculate. See here. When I'm reading, whatever signal is given, we are using for the PCM, and the accuracy, that means maximum accuracy is 0.1%. The analog voltage waveform has bandwidth. Again, FM we are having 100 Hertz and amplitude range. That means X max is ranging from minus 10 to 10. So here you will see that X max I am considering as 10. What we have to calculate? We have to calculate signal power. We have to calculate number of bits, data rate, and bandwidth. Okay. What I want trying to say that all these are related with bandwidth calculation. So number of inputs are given, and then you have to calculate its bandwidth according to the input given. So here you see in first step what you need to calculate. You need to calculate step size. So maximum error is given by mod of s by 2i mod. No negative value should be there. So step size always keep in positive mind. So always we are calculating step size in positive side and maximum error also in positive side. From that we are calculating the step size at 0.0.2. What is step size? Vh minus VL divided by Q. X max is my higher voltage and lower voltage. Hence VH is X max, minus of minus X max will become twice of X max, right? Divided by Q. By putting the value of Q, we are getting the value of N at 14 bits. Then from that, we have to calculate data rate, and from data rate, we have to calculate bandwidth. For calculating data rate, N, we are having FH is twice of F max. So by putting this value, we are having data rate, and bandwidth is 1 by 2R, that is 1400 Hertz. We are having bandwidth. And last numerical, as far as my PCM is concerned, here we are having difference of signal to noise ratio if input sinusoidal input given or normal input is given. So what is given? Let us see. So a PCM system uses a uniform quantization level followed by 7-bit binary encoder. So n bit value is given, that is 7. Then the bit rate of the system, that is small r, is given as 15 to 10 raised to 6 bits per second. What we have to calculate? We have to calculate bandwidth, signal to noise ratio. A frequency is 1 megahertz, right? Frequency of 1 megahertz. So there are two formulas. for single. First is 4.8 plus 6n and second one is 1.8 plus 6n. So by using these two formula, we have to calculate the signal to noise ratio value. So these are the which are dealing with complete PCM, delta modulation, error calculation, and bandwidth calculation. As far as PCM is concerned, if you are having any doubt, let ask me. Just I will brief what exactly we have covered. Okay. In the first phase, in the first discussion, we have covered all the digital modulation thing. What are these? PCM, DPCM, then delta modulation and adaptive delta modulation. What happened in the PCM? The end of encoding block depend on the value of m, the number of bits get generated. If more number of bits, more number of bandwidth and more number of bandwidth related to the more number of channel capacity. And then for reducing that bandwidth and reducing that channel capacity, we are using the DPCM technique. So in the case of DPCM, what happened? 2 bit per sample we are transmitted from transmitter to receiver. So as compared to PCM, the bandwidth requirement are less. Then still we require less bandwidth requirement. What we are doing in the DPCM 2 bit, instead of 2 bit, we are sending 1 bit per sample in the case of delta modulation. Hence, the number of bit count will reduce. That means bandwidth requirement are less, but data get corrupted because of the uniform quantization. So alternate solution is use of non-uniform quantization in adaptive delta modulation technique. So we can say that, we may say that adaptive delta modulation is best digital modulation technique for lesser bandwidth and for lesser channel capacity. All right. Then we are moving in this digital modulation scheme. What happened? Analog data input, digital data presented in the channel, and again in the receiver digital input is there and conversion will takes place. So there are certain calculations, formulas, numerical we have seen. Then next is the shift keying techniques. Okay, in the shift keying technique, input is digital, inside the channel analog data is there, right? We have seen 4 different shift keying technique. First is ASK, in which if data 0 is there, no carrier signal. If data 1 is there, carrier signal. Then we have seen FSK. There are 2 frequency level, low and high. If 0 is there, it will get multiplied by low frequency. If data 1 is there, it will get multiplied by high frequency. Then PSK signal, we are having phase shift. Whenever data changing from 0 to 1, 180-degree phase shift is there. If data changing from 0 to 1, 1 to 0, phase shift will occur. Then QAM. QAM stand for quadrature amplitude multiplexing, which is the combination of ASK and PSK, which will help in TV transmission purpose. Okay. Again, all these having some bandwidth. We have seen some numericals related to the bandwidth. Then we have seen the Hamming distance. Hamming distance is nothing but number of bit change between 2 bits. So we have seen some error correction, error detection formulas also, which will helpful in calculation with minimum distance. So that minimum distance is calculated by Hamming distance. And then we have seen some channel encoder, how this error created, detected, eliminated with the help of convolution coding. So these are all brief regarding your module 9, where all these points get covered. If you are having any doubt, please ask me. Otherwise, I will end here. Sumit sir, are you there?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay, okay. I'm just giving out of answer.
Okay.
It's a great privilege for me to express my warm and sincere thanks on behalf of Surya College of Engineering and Technology to Professor Ajinkya Nilawar sir for delivering the great lecture on digital communication under AICT sponsored Prerna scheme for the SCST students. We are pleased to hold this great lecture in our institute under the Prerna scheme for SCST students sponsored by AICT. Thank you, sir. Thank you all for your gracious presence. Thank you, sir.
Thank you. Okay.